lectures of what we call Saturday Science lectures, which are sponsored by the Department of Physics and Astronomy at LSU and the East Baton Rouge Parish Library. This is a program that has been running for nearly 30 years now, one Saturday a month during the academic year. One of the faculty members at LSU gives a talk on their area of research to sort of introduce to the general public, and particularly our targets are the school students, high school students, so that they know what is going on in different fields of science and engineering at LSU, and generally as general interest in science and engineering. And we are very happy that some years ago, the East Baton Rouge Parish Library joined with us, and they've been hosting it in this very nice hall now. And unfortunately, of course, with COVID, we have been offline for a little while, but we had a couple of sessions on Zoom. But today we are glad to be back in person. So it's very nice to see all of you, and you can look forward to other talks. Almost every month, roughly the second or the third Saturday, there will be a talk here at 1 o'clock. This semester, there will be a series of talks by faculty from my own Department of Physics and Astronomy, and we are starting with a good friend and colleague of many years, David Young, who is an alumni professor of physics, a senior professor in our department, and who works in the area of materials, he grows crystals and things like that, and then we characterize them. And in his teaching, he teaches at a variety of levels, including freshman classes, large classes, much larger than this. And he's going to talk today about physics in sports. So during the talk, he might sort of invite some of the youngsters here, the school students, to come up to participate in some of the demonstrations he has. And if you do, as a bonus, the department has a little gift for you as well. So this is to encourage you to respond to David. But it's a great pleasure to introduce David Young.
Thank you, Ravi. Good morning, or good afternoon, I guess. Thanks for swimming in. It's nice to see the top half of your face anyway. And I'm going to talk about something that I really know nothing about. So I applaud your courage in coming out and to listen to me talk about this. I guess I should say that kind of the interest in analyzing the physics of sports sort of came out of the digital marketing department at LSU. And so kudos for them for trying to connect athletics, which is very popular at a university like LSU, to the academic side. And so people sometimes, they just have a fascination with the physics behind sports, especially football, gymnastics, for example. The Olympics obviously were just this past summer, so it generated a lot of interest. So if some interesting sporting event, thing happened, the kick of a field goal that wins a game, they send me an email. Can you say something interesting about the physics behind a field goal? It's like, okay, well, let me think about it a little bit. Okay, so just as an outline, I'm going to talk about just sort of our goal today, what we want to try to get through, and my disclaimers. Come on, clicker. There we go. Okay. So we're going to look at projectiles. So a lot of sporting events involve throwing things, launching things into the air. And first we'll look at it without the effects of air resistance, because that's really easy to understand, or a lot easier anyway. Then we'll look at some of the effects of air resistance on objects. We're going to talk about some people that jump, so in particular high jumpers and pole vaulters. And then also people that spin. Okay, so these would be people like figure skaters and gymnasts. If there's any time, I'll talk about some of the impacts of material science, which is my research area on sports, and in some concluding remarks. So our goal, well, first my disclaimers. And so as Dr. Rao said, I am not a sports scientist. I am not a sports engineer. I do not have a degree in biophysics or an advanced degree in kinesiology. Some of my former coaches would probably say I barely have any athletic talent, actually. But what we want to do is, basically our goal here is to analyze some of the physics involved in sports. And so what that means then is to describe, or basically what we're doing is describing the motion of objects near the surface of the earth. Okay, so that's what we want to do. And by objects here we mean people and equipment. Okay, and they are big and slow objects, right? And so by big, I mean they are big compared to subatomic particles, and they are slow, or they move slowly with respect to the speed of light. So in the course of determining how we want to analyze these guys, I'm not going to have to worry about cosmology and astrophysics. I won't have to invoke any of the postulates of quantum mechanics, general or special relativity. Okay, so good old classical physics of 300 years ago, Galilean and Newtonian physics will be fine for the analysis that we want to do. So, projectiles 1. Many sports involve the throwing or launching of different kinds of equipment into the air, and so I've just grabbed some pictures of different ones that you'll recognize here. And as we'll see, oftentimes it's the human body itself, right, that might be the projectile. And so people are actually launching themselves into the air, jumping or jumping off of diving boards, for example. And so the motion of these objects as they rise and fall near the surface of the earth is something that we refer to as projectile motion. And once the projectile is launched, or once the person jumps in the air, then the only force that acts on them, okay, again, we're neglecting air resistance here, is their weight. So rockets, missiles, airplanes, those are not projectiles, right? Because there are other forces that act on them besides their weight. They have engines, for example, that provide thrust. And I guess I should replace my Challenger picture there, right, for the space shuttle with the SpaceX rocket. So when I was in high school, that was the 80s. And so the shuttle program was my space program, right? But now it's SpaceX, which is great. And of course, probably all of you know they just launched 4 citizen, right, non-astronauts into space. And I think they're set to come back today, right? Or maybe, are they back yet? Not yet, okay. And isn't one of the people from Louisiana? Yeah. The last name Arsenault, then you're pretty convinced, right? So an object's weight is the force that acts on it, and is a result of the acceleration due to gravity near the surface of the earth. And as you know, right, Newton's universal law of gravitation pulls every object near the surface of the earth towards its center. So just did they say there would be no math? Uh-oh. Well, we'll just do a little math. So you recognize Newton's universal law of gravitation. So the attractive force between two objects is equal to big G, right, the universal gravitational constant, times the product of the two masses, m1, m2, divided by the separation distance between their centers squared, right? And they refer to this as an inverse square law. So on the surface of the earth then, m1 would play the role of our object, the football, the person, okay? m2 is the mass of the earth, and if you're standing on the surface, then r becomes the radius of the earth. Then Newton's second law, right, which is another very famous relationship in physics, says that F is equal to ma. Okay, so you apply a force to an object, the amount of acceleration you get depends on the object's mass. Okay? And you might say, well, how can you set the gravitational force equal to ma? Because the masses technically don't represent the same thing, right? In the gravitational force, it is the gravitational mass and how gravity affects masses. And in Newton's second law on the far right side, that's what we refer to as the inertial mass. There's no reason a priori why those two should be equal to each other, okay? But the best experiments that people have done have shown to very high precision that they are indeed the same. Okay? So if we do that, then m1 cancels, and we have an expression then for the acceleration of gravity near the surface of the earth. And we can calculate that. And what it shows you is that the acceleration is constant for every object, right? So in other words, all objects fall at the same rate near the surface of the earth. So let's do the calculation, plug in the numbers, and you find that the acceleration due to gravity at the surface is 9.8 meters per second squared, okay, or 32.2 feet per second. And refer to that as little g. So what projectile motion is then, right, near the surface of the earth, is you have constant acceleration little g, in the vertical direction, and no acceleration, I guess you could call it constant as well, but it's 0, right, in the horizontal direction. So for projectile motion, it's accelerated motion in the vertical direction and motion at constant velocity in the horizontal direction. And because of then it results in the familiar parabolic path, right, that you see that projectiles take near the surface of the Earth. So let's start off our projectile motion by looking at a punt in football. So let's see if this will play. And the kicker here is Marquette King, and he used to play, he may still play for the Raiders. Let's see if this will run. I may have to click it up here. Did you guys see that? So that was quite a punt. Oh my goodness, what is that? Look at it one more time. Boom. And so you can see the beautiful parabolic path that the ball follows. So we'll come back to that. And so let's look at it a little more closely now. Let's break this motion down. And so again, we're analyzing projectile motion, and I've shown the football. You can see it there at the very top, right at the peak in its trajectory. So we'll draw in the parabolic path, and I've chosen a coordinate system over there. So the y direction, right, is typically chose to be upward. We'll do x left to right. Okay. And we want to just look at those velocity components at different positions along the trajectory. So in the first position at spot 1 here, oops, there we go. The velocity vector of the object, so now I want you to think about the complete velocity vector, is going to be a line, or it's a vector that's tangent to the particle's trajectory at that point. And so in this case, at position 1, the velocity vector would look like this. And we can break that velocity vector down into what are called vector components. One is along the x direction, or the horizontal direction, and one is along the y direction. And we've labeled them there v1x and v1y. Okay. And the thing to note is that the horizontal component is equal to what's called v initial x, right, which is the initial speed it had right when it was kicked. Okay. And that remains constant throughout this motion because there is no acceleration to change that velocity in the horizontal direction. So remember, acceleration, right, is changes in velocity. If you're in your car driving at constant speed in a straight line and you want to accelerate, you press the gas pedal, which is known as the accelerator. Okay? And so that would change the velocity. So the thing that's changing in this case is the y component only. And so let's look at a second position. So now the velocity vector v2 is tangent to the trajectory. And if we draw in the components, there they are. And so notice v2y now has gotten smaller than v1y because it has slowed down, it has decelerated in the vertical direction only, but our x component is still the same as it was before. It hasn't changed its length. Now we get to the peak, the maximum height in the trajectory. The velocity vector is now completely horizontal, and so the speed instantaneously in the y direction is now 0. So gravity has slowed it all the way down in the y direction to 0, and the only thing I have left is the horizontal component, which is always constant. Finally, then we come on our way back down, and so now I still have the x component, which is the same as it always was, but now the vertical component is increasing again, but this time in the negative direction because gravity is still accelerating it. Okay, so here's the kick one more time. Now you guys can't hear this, but the announcer said, "Holy smokes," when he kicked it. And then you hear someone say 528. Okay? And what that means is 528 is he means 5.28 seconds. He's reading off the hang time of the punt, okay, or the time of flight. So it was 5.28 seconds. And the range, if you look at it on the field, well, I won't go back, but it was 75 yards. So he kicked it from the 30-yard line on the other side, the other half of the field. So it has to go 20 yards first to get to the 50. Then another 50 yards to get to the other end zone line. Okay. And then it landed about 5 yards deep in the end zone. So that was a 75-yard punt in the air with a 5.28 hang time. Okay. And using our equations for motion with constant acceleration, we can derive relationships to calculate what the time of flight is and what the range is. And notice that they depend on the initial speed, v0, and they depend on the launch angle, theta, which is measured relative to the horizontal or x direction. So can we use these then to calculate what the launch angle is and the launch speed, since we know what the range is and what the time of flight was? I think we can. And so I started doing this, and it got a little complicated because I wasn't sure where it would go, just playing with it. But I solved that first equation for v0, right? Hopefully you can see how you would rearrange those, and then I square it. And the reason I do that is I'm then going to plug that expression in to my second equation for delta x and get rid of the v0 term. And then I'll just have a single equation that's left that just depends on theta. And so we get this. So sine 2 theta over sine squared theta equals the stuff on the right, and I know the value of those things on the right. So I can plug those in. There they are. So 75-yard kick is 68.6 meters when you do that length conversion. Our time of flight was 5.28 seconds. We square it, and the acceleration due to gravity, little g, is 9.8 meters per second squared. And oddly enough, that just turned out to be almost equal to 1 exactly. Okay, just a coincidence. So that makes it easy then. I need to solve this equation. So sine 2 theta equals sine squared theta. And so they said there's going to be no math, and now we've already entered transcendental equations, right? Because there's no simple way to solve this. Okay. But we could use computational methods, numerical methods, trial and error, right, which goes by the technical term guessing. Or we could use graphical. And so graphical turned out to be pretty easy. So I just went ahead and graphed these two functions. And so if you know what Wolfram alpha is on the computer, good for you. It's fun to go there and play around with it if you haven't before. Okay. So this just shows you sine 2 theta and sine squared theta. And wherever you see a red dot, that's a solution to that equation. Okay. So you notice there's a solution at 0. So I should mention that the x-axis here is in a unit called radians, okay, which is related to degrees, right? It's a measure of an angle. And it turns out there's actually an infinite number of solutions for this because pi is a solution. So you see the 3.14 there on the horizontal axis. And in fact, any integer multiple of pi solves this solution. But the one we're interested in is this guy right here, because that corresponds to our physical angle at which we kick it. And so that was 1.107 radians. And if you convert that, there's 2 pi radians for every 360 degrees of rotation. It's a launch angle of 63.4 degrees. Okay. So I apologize that got complicated. I didn't mean for it to. And so now, though, that we have the launch angle, it's easy. I can go back to one of my first equations and solve for the initial speed. So we plug in our values, do the calculation, and we find it's 28.9 meters per second. If you convert that, it's around 65 miles per hour, which is reasonable. Okay. Now, again, this is neglecting air resistance. If you actually measure very carefully the speed of the ball coming off of an NFL kicker's foot, it's actually closer to 85 to 90 miles per hour. Because of the air resistance, right, the range is going to be reduced, the time of flight and the maximum height are going to be reduced. So we can calculate the max height now. Let's do that. So again, plugging in the value for our angle, and we get 34.1 meters. So just looking at this picture now, again, I've sort of stopped it, right, with the football at its maximum height. And so we just calculated a value of 34.1 meters. So if I just say, okay, there's our distance. That's equivalent to 37.3 yards, which is around 112 feet. Okay. So is that reasonable? Well, I've got another scale, right, with since the football field is right there. So if I just take that length and rotate it horizontally and lay it down on the field, sure enough, it's pretty close. Okay, now it's not exactly because we're off at an angle a little bit, but it's not bad, right? And so I used to punt in high school. I never hit anything like that. Okay, 5.28 hang time at 112 feet. That's why he's a professional. Okay, so let's look at another famous projectile motion problem, which is called the monkey hunter. Now, I guess technically I guess hunting is a sport, right? This is Louisiana. But is it really a sport when one team doesn't know the rules? I mean, anyway, but this is a famous problem. And so the idea is that you have a gun, and you want to try to shoot a monkey who's hanging in a tree. Okay? But the thing is, I know, it's sad. And I will say that while this is a very kind of a time-honored problem that appears in many physics textbooks, I think Pete has gotten involved, because when you look at now newer textbooks, instead of shooting him, what they actually do is throw him a banana. And so that's what we'll do that. We'll launch him a banana. But it's the same thing. Okay. But the important point is that the minute the gun goes off or the banana launcher goes off, the monkey gets scared and he lets go. Okay? And so then if that's the case, then the question that we always ask, our intro physics courses is, which path should I aim in order to guarantee that the banana actually hits the monkey? Okay? Should you aim along path 1, which is at some position slightly above the monkey, aim path 2 directly at him, or path 3 slightly below him? Okay? And it turns out that you want to aim directly at him. And we'll try this in just a second, but just to show this to you, I'm not going to take you through every single step here, but get these to come up. So think about what we would need to do, right, to show that it's going to hit the monkey. So the point is, once the banana travels the horizontal distance it needs to get over to where the monkey is, okay, we can calculate the height of the banana at that position. And what we want to do is then show that the monkey's position vertically is exactly the same as the banana's at that time, which means that they will be at the same place at the same time. So using our equations again, this is what it would look like to go through this. So basically, these steps are just what I said. We're solving for the time it takes to cover the banana to cover its horizontal distance x, and then I plug that time into its equation for the final position of the banana in the y direction. And none of this is that important. The point is, here's the expression that you get, okay, the thing on the right. So now you do the same exercise for the monkey, and you solve for his final position. So all we're doing now is using the same equation for motion, but this time for the monkey. We know what the time is. That was determined by the banana's horizontal motion. I plug that into the monkey's equation for his vertical position, and notice, lo and behold, we get exactly the same position in the vertical direction. Okay? So it does check out. All right? So let's try this. So I have this kind of complicated looking setup, which does exactly what we want to try to do. Okay? So you need to tell me whether or not we want to shoot the monkey or a squirrel. So I actually did this last week for my class, okay, and I asked them that, and I got a resounding the squirrel. It's like, okay, do people not like, I know they probably eat squirrels in Louisiana, but, all right, so we'll try the squirrel. So this is a metal plate, and I have an electromagnet here. And I'm going to hang Chip or Dale, whoever that is. I'm going to hang him here. Okay. And then this is my gun, which is basically a large spring that shoots these hard rubber balls. Okay. And so it's not that advanced, but it does come with a laser sight, which is cool. Ooh, we're already almost lined up. Look at that. So we can see the dot, so I'll move it a little bit. There you go, little guy. And if you shoot squirrels with a laser sight, that is not sport, okay? Just saying. All right, so now we'll load it. think I moved it actually, didn't I? It went up a little bit. Okay. A lot of times I guess I should tell you how this works. So there's a photo gate, which has a little infrared sensor here right at the muzzle, right where the bullet comes out. And so when the rubber ball passes, it breaks that photo gate, which then temporarily disengages the electricity to the electromagnet and causes the plate to fall. So it exactly simulates the problem that we just talked about. Okay. So I'm going to go ahead and arm it, and hopefully it won't fall off. Good. And so now, and I should say that this gun doesn't shoot very fast, right? So you will see a nice arc to the ball. And the whole idea is just kind of watch everything globally. And the point is, hopefully, that by the time the rubber ball, gets over there, that horizontal distance, it will be at the same height. Okay, so here we go. 1, 2, 3. Oh, yeah, it's perfect. Oh, good catch. All right, so let's get a little cocky and let's move backwards a little more. And so if you look at those expressions, right, there is a solution, right, for any value of x, for any value of v naught, except 0, of course, if I don't fire the gun. Okay. But you might say, well, what if the monkey's too far away, right? In other words, you could imagine that there's not enough muzzle velocity and the ball would hit the ground before it gets to the monkey. Okay. Is that not a solution, right? But remember, the math doesn't care, right? It doesn't know anything about monkeys, bananas, physicists, guns, balls, none of that, okay? So that whatever muzzle velocity you use here, that will solve those equations. And so you could imagine, right, that we fired at something at a slow speed that would hit the ground. But now remove the ground, forget that the ground's not there. Okay? And imagine that we're firing over a large canyon or something like this. That problem would still continue, and eventually the ball would land where the monkey is vertically over there. Okay? So the ground is just a physical constraint that has nothing to do with the mathematics that comes in. Okay? And of course, if I were to launch the gun vertically, that would correspond to a theta of 90 degrees. And of course, cosine theta, cosine 90, do we know, anybody? 0, thank you. Physics students are on it, okay? And what happens when you try to divide by 0? General relativity people tell you bad stuff happens when you divide by 0, right? And so that's not a solution. Obviously, the bullet would never if you fire it straight up. Okay? All right, so let's do the monkey this time. Let me disarm it. Okay. We'll sight him up again here. Oh, it's already up there. It's way up there. Oh. Right in the face. Okay, perfect. No animals were harmed. So conceptually now, is it going to hit at a higher position, the same position, or at a lower position? Should hit at a lower position, right? Because it's going to take longer to get there. Therefore, both the ball and the monkey have a greater time to fall, a greater distance. All right, arm. Good. Here we go. 1, 2, 3. Oh, got him. And so another thing that it tells you is that, for objects like this that are small and that are moving fairly slowly, right, near the surface of the Earth, that using the approximations of no air resistance works very well. Okay. And so I mentioned, I showed this before. It's kind of hard to see. But you might think, well, how would a bowling ball, or what does a bowling ball have to do with projectile motion? And I just happened to run across this gem. This is great. Yeah. And then, oh yeah. So, so that's not how you bowl, that first case, right? In the second case, if any of you have ever gone past the foul line where the lane is oiled, it is extremely slippery. And that is an example of lack of friction, which we won't really talk about today, but I hope that one was okay. All right, so now let's talk about some of the effects of air resistance, okay? Because air can have a significant effect on the motion of projectiles. So near the surface of the Earth now, you're not actually moving through a vacuum, right? But you're actually moving through 1 atmosphere of pressure. And the weight of the air is not negligible. Okay, so, if you just take your hands and you do this really fast, you can feel the air, right? And it's a fluid that moves around you. So do you know what the pressure is on the surface of the Earth? The air pressure? Anybody remember? 1 atmosphere. Right? Yes. How about in PSI, pounds per square inch? Yeah. Not quite, a little too high. 14.7, yep, pounds per square inch. So maybe you've seen, if you ever inflated a basketball or your tires, for example, right? On the outside, below the valve, it says like 9 PSI. Okay, and so that's what we would call the gauge pressure, which you're inflating that ball relative to atmospheric pressure. Okay. What does that mean, 14.7 PSI? That's 14.7 pounds per square inch. Okay, 14.7 pounds of force over every square inch of area near the surface of the Earth. So to let you know what that feels like, I have a rod here. I'm going to have you hold your hand like this. Just lay it on the table. Okay. This bar weighs 14.7 pounds. Has an area of 1 square inch. If it hurts, tell me to stop, okay? You all right? Can you feel that? How does that feel? It feels very heavy. So now there were 2 atmospheres of pressure on your hand there momentarily. Okay? So the point is that, why don't we notice this weight? Why don't we notice the 1 atmosphere? Would you notice it being gone if you went to the moon without a suit? Yeah, yes, you would. But why don't we notice it? We've always felt it. You were born in it, right? Homo sapiens have evolved at 1 atmosphere of pressure. Okay? If you hand a bag of water to a fish, what's he going to do? Hey, nothing, right? Because he's used to it. He lives in the water, okay? So it's no different to him. But changes in pressures, and that's the whole point, right? Changes in atmospheric pressure are important. Here's another simple example of this. I like this one because it's easy, but so I just have a rubber mat that's got a hook on it. If I just lay it on the stool, oh, try again. There we go. It's easy to pick the stool up. You might say, well, it's magnetic. No, it's not magnetic. Right? There's no magnets on here. So what's happening? Yeah. Yeah, so what is suction? That's a term we often use, right? Is there any sucking force? Is that what's going on? Not exactly, right? So before I place the rubber mat on the chair, there's 1 atmosphere of pressure there. And when I place the rubber mat, rubber, right, is flexible. And so it can kind of seal around the edge of the chair. So now when I try to pull up on it, the volume under the rubber increases. And the air pressure then, because it's sealed, decreases. So I have a lower pressure now under the mat and a higher atmospheric pressure on the outside. And so it acts like suction, but what's actually happening is the higher pressure on the outside is pushing and holding the mat to the chair. Okay? And if I'm getting 14.7 pounds per square inch, roughly, that's more than enough force to lift that stool. And if I lift the corner and let the air in, then it quickly equilibrates the pressure on both sides and gravity takes over and it drops. Okay? So fluids are important, certainly in the motion of projectiles and many other things. And we have to consider things like buoyant force, drag force, which is what we usually call air resistance, the Magnus force, the Bernoulli effect, Coanda effect, laminar flow, vertex flow, turbulence. And to analyze this, we can use a branch of physics known as fluid mechanics or fluid dynamics to do this. Usually if the fluid is a gas, we would call that aerodynamics, and if it's a liquid, we would call that hydrodynamics. And the point is then that differences in pressure within that fluid can affect the motion of objects. And just to show you that people actually do this kind of stuff for a living, here's a calculation of the trajectories of projectiles where air resistance is taken into account. And you notice that in some of the cases for the different variables there, which have to do with things like cross-sectional area of the object to the weight of the object, it has to do with the power of the exponent that's on the velocity of the object, which is important. And notice that you no longer get the nice symmetric parabolic curves. Of course, you know, militaries are interested in this. If you're lobbing shells and bombs at people, those are being done obviously in air, and so you would have to account for the air resistance. And so the math gets fairly involved. I know I said no math, and I want to throw this up here. This is from that paper. This is why I didn't really take fluid mechanics. It's hard, okay? And look at all that stuff. Wow. So yeah, calculus is very important. So let's look at golf balls. So any golfers? The young guys are like, yeah, I golf all the time. I try to golf, and it just doesn't go well. So here is kind of a picture of one of the oldest golf balls. Golf is old. Look at that, 1400, okay? And it was made of wood. And it wasn't very aerodynamic, but it worked. And so then 1848, so 400 years later, there's the gutta percha ball that they use, which is made out of a tree sap, actually. And it was lighter, it worked well, and you could easily form it into a sphere, and it would harden up. And as you use the balls, the golfers use it, of course, it would become damaged over time. So it would become scarred, and it would become pitted. And what they found was that it actually went further when they hit it, when it was damaged. And so because of this, they started intentionally damaging the new balls, pitting them and scarring them before they would hit them. Okay. And so this obviously is, you know where I'm going, right? This led to, of course, what the modern day golf ball looks like, which has all these dimples on the surface. Okay? And dimples are important for golf balls. So here's a picture of airflow around a golf ball that is smooth. And what I want you to notice is the large pocket that exists back here behind the golf ball. Okay? And so when you have a smooth surface like this, you get basically something that's called laminar flow. Let me slow this down. And because of that, the air likes to stay in regions of faster speed because that's lower pressure. Okay. And so the air boundary layer here is what they call delaminates from the surface of the ball sooner, right, closer to the top and bottom of the ball, which creates this large low pressure region behind the ball. Effectively, and that's what causes the drag, right? Because just imagine you've got higher pressure essentially pushing into that low pressure region. Okay. So if you want to eliminate your drag, you want to try to minimize the volume of space behind the ball. And so this is where, the dimples come in. Because of the dimples, now you get turbulence, you get vortex motion of air here. And the result of that is it reduces that point at which the delamination occurs. So notice now that the air streams continue to move along the back of the ball further, and that reduces the pocket behind there. Okay, and so this is the explanation for why you get a greater distance out of a dimpled golf ball than one that is smooth. So here's a video of, this is the research and development unit out of Titleist, who makes golf balls. And so they made a golf ball that's perfectly smooth, and they gave it to some professionals to hit. I apologize, you guys can't hear that so well.
How far can I hit this? Well, I've never hit a ball without dimples, so I'm just going to guess. On the 40 yards, on the 30 yards? No dimples, I'd say 200 at best. Or does it explode? Well, if it gets up in the air, it's going to go further. Would it be a good idea to lock it? It's like an egg. It feels like when I hit this, I'm going to smash my club face for some reason. Is it going to get up in the air? Oh, right, disgusting. I think you got 200 there.
What's funny is these drives look like my drives with dimpled golf balls, right? So. So let's look at another effect due to the motion of air, and that's the Magnus effect. So here, let's say we have a tennis ball that's moving in this direction, and it's spinning. So the air is rushing by from left to right. So notice on the top side of the ball, that surface of the ball is moving in the same direction that the air is flowing. Whereas below the ball, the bottom surface of the ball is rotating in a direction opposite. And what this does is it causes the air above the ball to cling to the ball's surface and get directed downward. Okay. And so you can talk about pressure differences and things like that, but it's easy to understand if you think of this in terms of Newton's third law, okay, which you know is law of action equals reaction, right? So whenever an object applies a force to one object, that object must apply an equal and opposite force to the third. And so in this case then, since the air is being forced downward, right? In other words, the ball, because of this motion, is applying a downward force on the air. The air, in response, then, has to apply an equal and opposite upward force on the ball. And so what you get, then, is you get sideways forces that act on a spinning ball, okay? And the force is perpendicular to the direction of motion of the ball. In this case, it would be the yellow arrow upwards. And it's also perpendicular to the direction of the axis of rotation, which would be a line that's perpendicular through the ball and the screen. Okay. And so the Magnus force comes into play in a lot of different areas, a lot of different sports. Baseball is one. Soccer is another one. Golf, of course, and I'll show you some of these. Ping pong is another one. Okay. And so the first couple you're going to watch here is a curveball in baseball. And so how do you throw a curveball? Anybody? Can you show me? You got me? Ooh, that's almost like a knuckleball. Okay, how would you hold your arm? How would you bring it down? Good, there you go. Good. That's all I wanted to see. Perfect. Right? So do you see how he came up over the top? So when you throw a curveball, a lot of times they'll hold it, two seam like this, and they come up over the top and then snap their arm down like you're pulling a window shade down. And that gives the ball top spin. Okay? So now think about the Magnus effect. So I have top spin, the ball is moving this way. So now it's the top side of the ball that's moving opposite the direction. The bottom side of the ball is rotating in the same direction that the air is flowing. It's going to cling to the ball around the backside, and the air will get deflected upward from the bottom towards the top. Okay? Newton's third law says in that the air will apply an equal and opposite force on the ball, and it causes the ball to drop. Okay? Now, if you come straight over the top here like this, then the ball will loop, and it kind of looks like it's following a parabolic path, just like 2D projectile motion. But you get a greater amount of drop, right? And so the pitchers are really good at this, so that they kind of get the greatest drop right near the plate, right? And they say, oh, he drops the hammer, or it just falls right off at the end. Okay? Other times you can come, and instead of coming directly over the top, you come at an angle, like this. So now the axis of rotation is tilted this way. So instead of the force being directly down, it's now kind of at an angle. And so this causes the ball to curve from right to left away from a right-handed hitter, because then it makes it hard to see. And of course, you know, again, hitting a baseball, if you've never hit a baseball, it's really hard to do. And for major league pitchers, you know, as a batter, you have about half a second to make a decision on whether or not you're going to swing the bat, right? Otherwise, it's too late. And so a lot of times that curveball comes in, it starts way out here, and so you think from your eye, it looks like, okay, the ball is going to be high and out of the strike zone. So you kind of back like this, and then it breaks at the end, goes right over the plate, and you look foolish, right? But so that's the point. But really good batters, you know, they claim to be able to pick up the ball right off the pitcher's hand. And they can tell, right, from experience, sort of the motion of the arm, maybe whether or not it's going to be a breaking ball. Okay. So let's look at some of these.
Cycle those. Now the 2-2 coming. Breaking ball, call strike 3. Yes, no. Couldn't pull the trigger, and he is gone on strikes.
Oof. Oh. Okay, so I gotta do soccer, or football, okay? So, bend it like Beckham, right? You've probably heard of that. I think there was a movie that was that way. So again, when you kick the soccer ball, you can put a spin on the ball, okay? So then it travels, there will be a Magnus force that can cause it to bend. That's just nasty.
Kind of rough. I mean, it looks like he's aiming 50 yards left.
Okay, so here's Tiger. And so the flag is over here, okay, around that tree. And so what he's going to do is hit a slice. Okay, and again, without air pressure, the effects of air resistance, you can't do this, right? Because once the thing gets launched, it would just travel in a straight line. So there must be additional forces besides gravity that are acting on the object to get it to curve when it's in flight. And that's all due to the air pressure differences. So he's going to hit a slice, which means he's going to come down here and cut across the front of the ball, so that when the ball is launched off the club, it is now spinning this way. And again, that's going to cause a Magnus force to try to bend it, to slice it around. Okay, you know, and like I said, I hit slices all the time unintentionally, and the ball takes off. So he has a couple of these, which are pretty good. And then at the end, he's going to hit a draw shot off the tee, and they actually have the ball tracker on it. You can see it. And in that case now, and so notice he'll finish here, and you'll notice this especially in the second one that he slices out of the bunker, that the way he finishes, he comes down and he's cutting across the ball like this to get it that spin. In the last one, he'll come across and actually turn the club over, which causes it to spin this way, and that's how you get the draw. Okay, or in my case, a hook. Oops.
Cycled up.
It's a roof here with a goal. I don't believe it. David Beckham scores the goal to take 8.
Kind of rough. I mean, it looks like he's aiming 50 yards left.
Oh, it's not a cut. That's a slice. And it's a good one, too.
Look how he finishes.
This is Tiger the artist.
There's the draw. Look at that. Okay, tennis. Got to have Roger Federer. Look how he slices across the ball.
In full control, the opening 13 minutes of set number 2, 3 games.
I miss Sharapova. She always yelled. It was great. Look at the slice here. Doink. Woof. And see how the ball takes off when it hits the ground because all that spin it's got on it. Look at that. Ping pong ball. He hits down on it, right? So it's got backspin. This is like a rising fastball almost. Look at that one. Jeez. He'll show it in slow-mo. Curve. Okay. How are we doing on time? Because geez, I'm never going to get through all this stuff. Okay. That's all right. So let's look at some jumpers for a second. And here we're thinking about just energy, right? And so you can broadly classify energy as one of two types: kinetic energy, which is energy of motion, and potential energy, which is energy of position. And so here we're interested in translational, right, or linear kinetic energy, which we calculate as 1/2 mv squared, so it depends on the mass of the object and its velocity. And the potential energy here we're interested in is the gravitational potential energy. And so just by varying your position near the surface of the Earth, you can change your gravitational potential energy, which also depends on your mass and the height you are above some zero location. Okay. So let's look at the high jump. And I'm trying to include some of the LSU students athletes who we've looked at before. So this first athlete is Abigail O'Donoghue. And she set a record, a school record. And so obviously you're running, so you're increasing your kinetic energy, and then you're going to convert some of that kinetic energy into gravitational potential energy. So, the goal of the high jump is very easy, right? Just jump over the highest bar you can. And notice the way in which she does this. So once she leaves the ground, the maximum height for her center of mass is set. Okay? And because conservation of energy dictates that to be true. And so if you're just standing here and I ask you, where is your, my center of mass? And center of mass, right, is a rough estimate of the overall mass in the system. So I'm not, a nice geometrically symmetrical object, okay, but the majority of your mass is kind of here in your torso. So your center of mass is roughly here, maybe around your hips, your belt buckle, etc. Okay? But by positioning yourself, by changing your body's position, I can change the location of my center of mass. Okay? Just putting one arm out and keeping this arm down changes the location of my center of mass, shifts it a little bit more because now I've taken some of my mass and moved it right away from my center line position. So by her getting in this position here, which is the famous Fosbury flop that was first used by Dick Fosbury in the Olympics in 1968 in Mexico, to go over the bar this way. So now notice that she has a lot of her mass, her body's mass, underneath the bar. And that lowers the position of her center of mass. And so by changing your body's position, it allows you to clear higher bars, right, without actually having your center of mass pass directly above the bar. Right? And pole vaulters do this, and we'll show that as well with Mondo here. Oops. So this is Mondo Duplantis, and he just won the gold medal in Tokyo. And so again, he starts fairly far back from the vaulting area, gaining his kinetic energy, and then he plants. And notice that in this case now, he jumps, but not as much, not like a high jumper. And so when he comes in, he'll plant the pole, and he turns that translational kinetic energy he has into stored elastic potential energy inside the pole because it's flexible like a spring. Okay? And then he'll get that stored elastic potential energy back at a later time during his jump. Just incredible. I mean, if you've never pole vaulted before, go try it and see how that works out for you. And notice, he does a similar thing by changing his body's position, right? So that he goes over the bar in a bent fashion like the high jumpers do, but he goes over feet first and face down. But still, his center of mass, right, can be kept in a lower position, okay, which allows him to maximize the bars that he can clear. And what's interesting is, we're talking about projectile motion too. He's not technically not a projectile until right at the moment he lets go of that bar at the top. Then he's a projectile. Okay? And so he pushes away, throws the bar out so it doesn't hit, throws the pole out rather, it doesn't hit the bar. He caught the bar a little bit with his wrist, but it stayed up there. And so he was okay. Okay, so athletes, gymnasts, divers, right, they do a lot of spins and a lot of flips. And for linear momentum, that's a quantity that is equivalent to the product of the mass, right, which we would call sort of the linear mass, right, little m, times the translational speed. And so P is equal to mv. But we could also talk about angular momentum. So just imagine that you had a wheel that's rotating, okay, just spinning but not moving translationally. It, of course, would also have some momentum and rotational energy as well. And so that's going to be equal to angular mass, whatever that is, times angular speed. Okay? And so angular momentum is typically represented with a capital L. The angular mass is this funny thing called moment of inertia. And the angular speed, omega there, is just how fast the object's spinning. Okay, so, RPM, right? Revolutions per minute, rotations per second. And so what is this moment of inertia? Well, it's what we refer to as the rotational analog of mass. Okay? It also depends on the mass of the object, just like our regular translational mass does. But more importantly, it also depends on how that mass is distributed about the axis of rotation. Okay? So you could have objects with equal masses, but they can have very different moments of inertia. And that will change then their angular momentum and thus how they spin and how they rotate. In general, for two objects of roughly equal size, equal mass, the one that has the smaller moment of inertia is easier to rotate. Okay? So I need a volunteer. Okay, come on up. So I have these two metal tubes, and I have a scale here. And see if I can turn this on. I want to weigh these, okay? And so by weight, right, that's going to be directly proportional to the mass. I just want to show you that they're the same. So we'll do the blue one. What do you got? There you go. 1396 grams, okay? And let's do the red one. What do you got? You can tell them, don't lie. 1397. Okay, so not exact. It's one part out of 1300. It's close enough. That's less than 1/10% difference. Okay. So now what I want you to do is hold them by the middle in one hand, and then hold the other one. The other hand. Turn around and face everybody. Okay. And now hold them out like this, and rotate them as fast as you can. Do you notice anything different? Is one easier to rotate than the other? Yeah. Which one? The red one. But they're the same mass. They're the same weight. Can you explain that? I can't either. I don't know. I'm just kidding. So inside, thanks, you can sit down. So inside there are two weights, right, on each side of the axis of rotation. In the red bar, they are very close to the axis. So we would say that this object has a low moment of inertia because the mass is distributed close to the axis of rotation. It's easy to rotate. On this guy, it also has the same two masses on each side of the axis of rotation, but now they are all the way out on the edge. It has a greater moment. It hurts your wrist almost if you go too hard, right? It's way out here. Okay? So same mass, same weight, but very different moments of inertia. And here's just, again, very similar explanation, but with a circular object. So you could compare, for example, the moments of inertia of a disk of mass m and radius r compared to a ring, a thin ring with the same mass and same radius r. The disk has a moment of inertia I that's 1/2 mr squared, whereas the hoop or the ring is actually twice as big. Why? Well, because it's got more of its mass distributed further away from the axis of rotation all the way out here, whereas the disk mass is distributed uniformly, and so much of it is closer to the axis of rotation. So angular momentum, as we mentioned, is the product, right, of moment of inertia times the angular speed. And we have this statement which says, in the absence of external torques that act on the system, the total angular momentum of the system is conserved, which means that product of I times omega has to be conserved in that situation. So what that tells us then is that if I have a system that can change its moment of inertia, then its angular speed or its rotational speed will also change to keep the total angular momentum constant. So for example, if you have a large moment of inertia, you will have a small angular speed, but then if you decrease your moment of inertia, then your angular speed would increase to keep the product equal to each other. So figure skaters do this all the time, right? When they spin, and so as they start to spin, you can look at their rotational motion, but then they do things with their arms and their legs. They change the position of them relative to the axis of rotation. So they're changing their moment of inertia on the fly, right, while they rotate. And you might say, well, is this really an example of a system where we have no external torques, right? It's pretty close in the sense that the ice she's skating on is fairly frictionless, right? So we're assuming that there's no friction that could slow the rotation down. So here you see a couple of these. So notice how slow she's going with her leg out, and she'll bring her legs in. And she does that, which I could never do. And notice how much faster she goes. So the next one's even better. So there's that's called a camel spin, I believe, right? There's a sit spin. Okay, arms out. Oh. Slow, slow, slow. Now she's bringing that leg in, and boom, look at that. Wow. Yeah, no, that ain't going to happen. Oh, I just happened to see this. This is a pair figure skater. And this is, again, an example of projectile motion. He launches her straight up in the air, and by the time she comes down, he's right there to catch her, right? And so that, again, is an example of two-dimensional projectile motion. Okay, very quickly, here it was, this is McKenna Kelly, who is an LSU gymnast, and she had a perfect 10 on a floor exercise. And this is what you get when you combine the DNA with a gold medal gymnast and an all-state quarterback. So I don't know if you know who she is, but her mother's Mary Lou Retton. So some of you might not know who Mary Lou was, but she won an all-around gold medal in 1984 in the Olympics. And her dad was Shannon Kelly, who was an all-state quarterback, and he played for the University of Texas. So she has some athletic skills. So this is on the floor exercise, and that floor, while it may look solid, actually has about 1,000 springs under it. And so it's really more like a trampoline than it is a solid floor. But notice here she's doing a round-off back handspring into 2 flips. Okay? And what I want you to notice is that she's not twisting, right? She's just rotating about one axis through her hips. Okay, and I'm trying to say that that's easy. But it is easier, right, compared to what Simone Biles does, okay? So she has a famous thing called the Biles, which is the triple double. So this is 3 twists and 2 flips out of a round off back handspring.
Just keep making history, Simone Biles.
So you can, it's so fast you can't even really see what she's doing, right? So this is 3 twists and 2 flips. So there's one axis of rotation which runs through her midline, and the flipping axis which runs through her hips, right? And she's twisting around both of those, okay? So here's my gymnast. He was more of a mental gymnast, but that's it, okay. He did ride a bike on occasion. So he will be rotating about an axis like this and rotating about an axis like this simultaneously. And so if I try to do that, I'm going to flip you and twist you. You can kind of see, right? There it is. That was it. The motion he has. And so he's got angular momentum about this axis. He's got angular momentum about this axis. And as he's doing this in the air, you can imagine that his total angular momentum vector is kind of wobbling around, okay? And so for her to do this, you know, and complete it is just incredible. So let's slow it down a little bit, and so you can see this. And I've made some comments in here, but so there's a torque that's applied by the floor. There's a static friction force that helps the launcher and get her twisting. And now once she's in the air, she's going to pull her arms across her chest. She's decreasing her moment of inertia about her vertical axis, right, her twisting axis. And she keeps her arms close in, okay, which reduces the moment of inertia to maintain a high rotation rate. Notice her knees are bent too. That lowers the moment of inertia about her flip axis, so she can keep spinning that way. Now she locates her landing spot, right? Notice she can see it here. And now she has to unwind all that kinetic energy to stick the landing. So the arms come out, the legs straighten, and boom, she hits. No, I would never try that either. So here's just some of the numbers. And again, this is, you know, people actually do this for a living. I'm just me fooling around with YouTube videos, trying to pull the numbers off the video that I see. And so these are some of the numbers that came out. So we could calculate, again, her launch angle, her speed at launch, her maximum height above the floor, the change in height of her center of mass. And we can calculate her average impact force using something called the impulse momentum theorem, which states that the product of the average force times the time over which it's applied is equal to her change in momentum, linear momentum. Momentum, again, is mass times velocity. Her mass doesn't change, so this is mass times her change in speed. And so for the change in speed, I just used the change in her velocity from launch to landing. Okay? And so to do that, you need a time. And so how long does the landing take, right? Well, you'll notice they put a cushion down there for her to land on, because what that does is it increases the time it takes to bring her to a stop, which reduces the impact force. Okay? And so, you know, just based on watching the video, I used basically 200 milliseconds, about 2.2 seconds, and I'm getting an average force of about 382 pounds. So it's about 1,700 newtons. So it's over 3 times her weight. So if you're squeamish, then you may want to close your eyes here. I'm going to show you an injury, but I just want to let you know, okay? So, yeah. This is Samantha Serio. This happened 2 years ago at LSU in the regional semifinals. She was doing this is her first pass on the floor exercise, okay? And she was somersaulting forward. So she comes across, she has to do a blind landing, right? Because she can't see because you're rotating forward. She under-rotated and broke both her legs and dislocated both knees. And yeah, if you want to watch the video, you can, but it's hard to watch. But the reason, you're like, why am I showing you this? Well, because when I was analyzing the gymnast stuff, this happened, right? So it was kind of I don't know, a sentimental moment for me. And so I followed up on her. And so she had surgery in April, like the second week of April of 2019. And in the first week of June, she walked down the aisle and got married. Okay. So it has a happy ending. She's at Auburn, was at Auburn, by the way. She was the co-scholar athlete of the year in the SEC, and she went on and is now an aerospace engineer with Boeing. So STEM people can be gymnasts, athletes, very cool, right? So she's like a great role model. Okay, I'm like way over time, huh? Yeah, all right. I was just going to show you one example of how advances in materials could have impacts in sports. Of course, you could think of many, right? The advances in golf balls, as we mentioned, golf clubs, composites, baseball bats, tennis rackets, all kinds of things. And this one's kind of interesting because it shows the world record as a function of time for the pole vault. And so what you'll see is that, it kind of goes along. There's increases, and then there's a lull. Then there's like missing data, right? Another lull, etc. And it shows you here, where the advances were made in the materials. Right? Notice what's interesting, right, is that, look, there's missing data here, and there's missing data here. Can you see why? Very good. Yeah. So, if you're a really good pole vaulter, then they wanted you to go to war. So World War I, World War II, we're missing some records. And I think most of this out here, I forget the gentleman's name. I think the advances in the record each year was due to one person only. He just kept getting better by himself. But the point is, you can see when they introduced fiberglass poles, these composites, that then the records started taking off. So I just happened to pull this off of the University of Oregon's business school, because they were looking at this as from a business aspect about performance, and so they use this as an example, but then looked at the automotive industry for something else. But it's just kind of interesting. Okay. Oh, I need another volunteer. Real quick. We want to demonstrate the moment of inertia here. This is a good one. Oh. Okay, come on up. Whoever wants to spin. We got some young? Yeah, here's a young guy. Come on up, bud. Here we go. This will work. All right, so have a seat. You okay? You're okay to spin? You're not going to throw up on me or anything? You don't think? I would. He's like, do you have anything to eat? No? Okay, good. So we just have a stool, and the stool will spin. I'm just going to spin you a little bit. Okay. And notice that it spins pretty freely, so it has pretty good bearings in it. And so the point is that we're approximating here a situation where the sum of the external torques on the system is equal to 0. Okay. And so what I want to do is, we'll see, pretty strong. Yeah, can you hold these in each hand? So I'm going to start you spinning, and I want you to keep your arms out here, away from your body a little bit. There you go. And then once you're spinning, then I want you to bring your arms in, close. So when you start out here, your moment of inertia is large, right, because you've got a lot of weight distributed far from the axis of rotation. Then when you bring it in, the moment of inertia goes down. This is what the ice skater's doing, right? Okay, you ready? And if you feel like you're going to fall off, just catch yourself. Whoa. Here, let's get you going again. Hold your arms out first. We'll start out first. You can put your feet on the stool if you want. Up there. There you go. There you go. Scoot back a little bit. There we go. Okay, so hold out. There we go. Bring them in. Whoa! That's all right. There you go. Thanks, bud. Let me see if I can do it without throwing up. It's amazing. When you get older, I tried to swing the other day. You can't swing anymore. I used to be able to. Okay, let's see. Here. Oh. Makes a huge difference, right? Let's try again. It's much easier out here. Stars do this too when they collapse, right? So, oh God, that's bad. Okay. So, that's my only concluding remark. And then just to show, if you're interested in this kind of stuff, right, there's tons of things that you can, resources on the web that you can go to. ESPN Sports Science, not sure they do new ones now. Veritasium is an excellent YouTube channel that probably some of you have looked at before. NSF, NBC Learn. So there's a professor at Southeastern, Professor Rhett Elaine, who I just happened in looking at things. He's done a lot of these really nice analysis, even more in-depth analysis. So you could find him too at their department's website. Thank you guys. Appreciate it.
I'd like to thank Professor Young and the graduate students of our department who run this program. In view of the hour, if you have any questions, please come up individually, but otherwise we'll close it. Thank you for coming, and the next meeting will probably be on October 9th, which is the second Tuesday, when there'll be another talk at the same hour at 1 o'clock.